Okay, ladies and gentlemen, so we're going to take a look at how we're going to solve equations involving sines, cosines, and tangents. So what we're going to do is we're going to start by trying to isolate the function as much as possible. And what's meant by this is that we need to take a look at trying to isolate the sine here, because the function here that we're looking at is the sine. So we want to try to isolate sine as much as possible. And when we take a look, we have 2 open brackets x minus pi over 6 that's inside the sine function. And so we can't start working on that just yet because we need to isolate the sine first. So the first thing we're going to take a look at doing is trying to get rid of the 2 that's multiplying the sine function. So as long as we do the same thing on both sides, we can preserve the equality. And so we're going to be working with sine of 2x minus pi by 6 is equal to the square root of 3 divided by 2, because we've divided by 2 on both sides. Now we need to ask ourselves, when we look at the unit circle, which angle values are going to give us a sine of square root of 3 over 2? And by looking at the unit circle, we end up finding that the angles, now the angles is what's inside the sine. The angles are always the arguments of our sine function. And so we're going to say that our angle, which just happens to be 2 open brackets x minus pi over 6, that is going to be equal to the first angle being pi over 3, and the second angle on the unit circle that gives us the same sine of square root 3 over 2 is 2 pi over 3. Okay, and that's just by observation from the unit circle. Now we have to keep in mind that the unit circle itself is repetitive. It repeats over and over and over again, and we know that the period of repetition for a unit circle is 2 pi. So we're going to write it not as 2 times x minus pi over 6 is equal to pi over 3, but we're going to account for that repetition by putting in this plus 2 pi n. I'm going to put a plus 2 pi n for the other one as well because it's the same thing. It will also repeat every 2 pi. Okay, and the n represents any integer. It doesn't matter what, but an integer is a number like -3, -2, 1, 5, 1,000. It doesn't matter as long as it's a whole number. So we're looking at pi over 3 plus a whole, or multiples of a whole revolution around the unit circle. Okay. So we're going to start to isolate for the x because ultimately that is what we're looking for. We're looking to find values of x here and values of x in this one here as well. So the first thing we're going to do is we're going to divide by 2 on both sides. So we're going to find x minus pi over 6 is equal to pi over 3 divided by 2 gives us pi over 6 plus 2 pi n divided by 2 leaves us with pi n. Okay? And we're going to add pi over 6 to both sides, so that's going to leave us with x is equal to pi over 6, oops, sorry about that, that's going to leave us with pi over 6 plus pi over 6 plus pi n. And pi over 6 plus pi over 6 is 2 pi over 3, 2 pi over 6, which is just pi over 3. So x is equal to pi over 3 plus pi n. And that's working with the leftmost equation. If we do the same thing with the rightmost equation, we'll find that x minus pi over 6 is equal to pi over 3 plus pi n. And now when we're going to isolate for the x, we're going to have x is equal to pi over 3 plus pi over 6 plus pi n. And when we combine pi over 3 and pi over 6, we have that x is going to be equal to 3 pi over 6 plus pi n. And 3 pi over 6 is just pi over 2, so we have that x is equal to pi over 2 plus pi n, where n represents any integer, like 0, 1, 2, 3, 5, 1,000. It doesn't matter as long as n is representing an integer, and that in turn represents a full revolution along the unit circle.